samples. For example, so where is it? This. Okay, so here we have some sample, red sample, and this is a ratio. Samples ratio is 1, so 100%. And the buffer is a kind of water, special water, to mix with samples. So the ratio is 0. And if we mix this, so as I mentioned, in this device, we move one droplet, and then we mix this, then we can have half ratios. And this volume becomes 2, and then we split this into 1 volumes. And so one of the droplets will be go to the waste pot, and one is remain in this device, for example. So in this case, so here the model of mixing is we have 1 by 1 mixing, and then ratio is of course becomes half, and we have 2 half ratio droplets. And in this case, one is going to waste pot, and one is still inside this device. And then, for example, we can mix this again with this 0. So we have quarter ratio, for example. So, okay. This is a very simple case also. But for example, if you need this ratio, then you need this procedure. And this is called sample preparation. And but in the okay, so this is a model. Okay, again. So probably if we have n droplets of this concentration and n droplets of this concentration, then by using n times of mixing, then we have a half concentration ratio, and we have this double volume of these considerations. So any questions so far? Maybe this is a model of my discussion. So if you don't understand this model, maybe you can't follow from here. So any question up to now? Okay, or any question? So for example, if your task is to generate this and this ratio, then this is called a dilution graph, where we want to generate these two ratios. For example, here, so okay, so this circle means the ratio is 64 over 64, and this is 0 over 64. But here we just omit these denominators. So for example, if we mix the 0 and the 64, then we have a half ratios, something like this. And this is a waste. So we have this 21 and 51, for example, eventually. So this is a very simple way of mixing, but if we have a, this is generated by called Lemire heuristic, which is considered as a very good heuristic. So as you see, so we have a same results, but here the number of samples, number of buffers is less than the left-hand side. So this is number of operations. So in these research communities, maybe for the last decade, so we want to have a design methodology to make this dilution graph with less sample, maybe sample of the numbers, because sometimes this sample is very precious, very expensive. Buffer is not free, but it is relatively cheap. So anyway, then okay, my talk is given this target direction graph. So we can consider some optimization problem to decrease the probability of error tolerance. Okay. So what's the problem in this area? So here, as I mentioned, we can move droplets. So if we have a high voltage here, so two droplets coming here, and then we can mix. So we have two volume droplets here, and then after that, if we give this and these two directories high voltage, then this large droplets is split like this. So this is the ideal operations. So here, so ideally it should be split in 1:1 ratios. But of course, this is just analog machine. So what happens here is that sometimes there is unbalanced splitting. So this is this table is from previous research. So here, of course, these values changes depending on the device, but they reported that this unbalanced splitting, this epsilon, almost half cases, this is 0%. But sometimes, for example, unbalanced 1% is with probabilities more than 30% occurs, something like that. Maybe this is missing, this is 3, should be 3. So this is called unbalanced splitting errors. Of course, this is not ideal. So, okay, so here we want to have these ratios, 87/128, and this is half. So by mixing this is ideal mixing, this black is waste. So if there is no errors, of course we have these ratios at the end. But for example, if there is unbalanced splitting here, then for example we have a larger one and a smaller one. If we use larger ones, then of course the ratio will be changed to this. And if we use smaller one, then of course ratio is changed to this. So this is the error. So our topic is how to deal with these errors. Okay, so far. So maybe practically this is a very good strategy. Is that so? We have a camera sensor on the device, and then camera sensor checks the volume. And if we split, then if there is a very big difference of the volumes, then we just turn back. So just mix two droplets again, and then split. And we check, the camera check the difference of the size, and we redo these operations until the split error is within the acceptable values. So maybe this is one solution, but this kind of solution needs cameras and also many retry operations. And this is interesting research from Sleep Powder. Actually, this is an Indian team. And so this is original direction graphs. And here, actually, there is a waste. So the idea is that by using these waste, they have same operations here. So meaning that this operation should be the same considerations. And of course, they have some errors here and they have some errors here. But if they do mix from these same things, then they can average errors. Do you understand this idea? So they may, for example, this is a larger and smaller, but they have errors and they also have errors. But if we average them, then maybe we can expect that the error should be decreased. This is an interesting way, and our work is maybe generalized of these ideas. So, any questions so far? Okay. Okay, so maybe I think you are in the computer science related area, so it is very easy for you. So for the fault tolerant issues,
responsible for unbalanced splitting?
oh, excuse me?
What are the reasons responsible for unbalanced?
Responsible?
Yes. What are the reasons responsible for unbalanced splitting?
Excuse me, what do you mean responsible? So what are the reasons of unbalanced splitting?
Yeah, like why it occurs. What factors are responsible for it?
Sorry.
Why does unbalanced splitting occurs? He's asking.
He's asking what?
Why?
Reason of
Why happens?
Why
reason
does
of unbalanced splitting. We want to know why unbalanced splitting occurs.
Why? Oh, why means.
What factors like that?
So actually, I don't know the detail of the device, but because this is just analog operations, so just mix is easy. If we have a high voltage here, then the two droplets come to this center. But when we want to split this, we give this high voltage and high voltage. Then ideally, this force to go to the left-hand side and go to the right-hand side is same, ideally. But of course, there should be some unbalanced. If the force to the left is larger, then the, so in this case, the force to the right-hand side is a little bit higher, then this happens. So because this kind of device is very, this is micro size, miniature, so this happens. That's not what I mean. I don't know the reason, but this really happens. Is it okay? So I think this is the only work which can do this kind of research. But after that, so we consider. So this is not research, but I just consider what happens in biochip designs. Because in the digital case, you may know that fault tolerant issue is very easy. For example, if you have one digital modules, whatever, then if your module outputs a wrong answers with probability p, then there is a good way to decrease these probabilities called triple modular redundancy. This is maybe very famous. That is, you duplicate these three and these output, and then just majority voting. Then wrong answers occurs, 2 of 3 gives wrong answers, which is something like these probabilities. So the probability becomes very small because p is still very small. So p to the 3 is very small. So practically this is okay. So for example, for the spacecraft, in the spacecraft actually there is some software. So they have this kind of scenarios, for example. So for digital case, it is easy, but for our case, so is it, for example, that kind of, this is, if we have two same droplets and then average, that is kind of duplications. But let's consider what happens for the duplication in our case. So there are so many scenarios, so I consider very simple cases. That is here. This is anyway, so desired concentration here. And maybe within some distance, that is okay, acceptable. And by problem P, the result is not unacceptable for our experiment. Then in this case, for example, within the desired value, the probability is 1 minus P, and more than that is probably P over 2, and less than that, P over 2, so totally 1. Okay, let's consider this scenario. Then, if we do the duplication like the previous research and averaging them, so two dilution graph outputs acceptable and acceptable in this desired values. Then if we average them, of course, we get acceptable, something like that. And one is acceptable and the other is larger than the acceptable, but still probably acceptable. So this is depending on the scenario, but something like this. If we consider this scenario, then in this case, both are larger than the desired value, or both are lower than the desired values, then we get undesired values. The probability is this. So this P becomes P squared, which is something like the digital case. So duplication works very well. But for example, in this scenario, that is, so maybe we have a very strict constraints. So one is acceptable, and one is larger, then we cannot accept the average of these. In this scenario, actually, the unacceptable probability is something like this. This is a simple calculation. So in this scenario, actually, this value becomes worse than the original values. So unlike the digital case, so analog case, in biochip design case, in many scenarios, in simple duplication doesn't work well. That is our motivation to do some specific solution for the fault-tolerant scenarios. So by the way, for TMR, actually there are so many scenarios we can consider. But for example, if we consider these scenarios, actually this also, in this case, correct value may be a little bit better than the original one, but not so good, almost similar. So maybe duplication in many cases doesn't work for biochip design. Okay, maybe I skip this. So this is very complicated cases, but in many cases, probably, so my first message is, for the biochip design, duplication doesn't work very well in many cases, unlike the digital components. And so we propose that a little different approaches than simple duplications. So method one is very easy. That is, so in this case, we also need sensor camera, but we don't need to redo operations. So our idea is very easy. That is, if our camera detects the unsplit, unbiased splitting, but we can detect which is larger or smaller. So we use larger or smaller one. We select to use further operations. For example, here, if we have unsplit error here, then we know that there is a 10% unbiased splitting errors. Then also we can calculate the final result if we use larger one or if we use smaller ones. So we can select which is better. Actually, the ratio is always different. So the error is always different. So we just adaptively select the better one. That is our method one. So this is very easy idea. But then this is simulation results. So this is a simple result that is without any error recovery operations. Then this kind of error happens. And this is a previous work that is if there is an unacceptable errors, then we reduce the mixing. So this is a number of redo operations. But error becomes very small. And our idea, our method doesn't need resplitting, but still better than the original one. So maybe kind of intermediate of the solutions. So, okay, any questions so far? This is easy. And actually, the second method is our main contribution. This is a little bit complex, but so in this case, we don't need any cameras, and we just consider how to make the dilation graph. Okay, so this is actually a dilation graph when we want to have this 36, for example. And here, this graph means that here we have two buffers droplet and two sample droplets, and then we mix. So this is a half ratios, and we have actually 4 droplets here, and 2 is going here, and 1 is going here, and 1 is waste. But in the reality, we cannot do this mixing because here we mix 2 and 2. But as I mentioned, in the device, we can only mix 1 and 1. So if we want to mix 2 and 2, in this case, actually we need to mix twice, 1 and 1 and 1 and 1. So here, actually this result go to node B and node other nodes. So we select this, which operation go to node B and other node. So here in this case, for example, so node B is also 2 and 2 mixing, but we need to determine, so we have 2 operations here, node B1 and node B2, and node B1 has 1 from 0 and has 1 from 32. But as I mentioned, 32 has 4 droplets, so we need to determine which one from 4. So okay, maybe it is not a good explanation, so I'll explain in the concrete example. For example, this is a dilation graph. Here we have, this is intermediate, so we have, this is some intermediate solution ratios. And we have 4 droplets here, and 1 is going to A1 and 1 is going to B1, something like this. And if we do this physically, then we need 2 mixing, X1 and X2. And then, for example, this is one case. X1's output is going to A1 and B1, and X2's output is going to C1 and D. But as I mentioned, we need to determine one of these candidates. This is a different case. X1's output going to A1 and C1, and X2 is B1 and D. Or X1's output is going to A1, D, and X2 is B1 and C1. So this means that from X output going to A1, B1, C1, D, there are 4 destinations. But actually, this is physically 2 mixing. So we can select which 2 is the output of X1. So A1, B1, or A1, C1, or A1, D. And this is not considered in the previous research because in these 3 cases, the number of operations, number of samples is same. So probably people doesn't care the difference. But we reveal that the error probability becomes different these 3 cases. So we propose that how to select the best one from these graphs. That is our main contributions. And of course, if we do the many simulations, among the different candidate graphs, then we can maybe select the best one. But that's very time confusing. So we introduce some concept which we call RRE to predict how how fault tolerant for each graphs. Okay, so this is the idea of RRE. Okay, this red value is RRE values. So the idea is something like that. So let's assume there is an unbalanced split here. Then that means that one of them are larger and one of them are smaller. But interestingly, for example, if here we have additionally 10 milliliters, but here this is mixing and half becomes half, which means this larger portion becomes half here. Do you understand? This is the idea of our method. And also this error amount becomes half again here. So by each mixing operations, this error becomes half and half and half. So we put these values. So these values is the coefficient to estimate how this error impact at this point. So for example, this means that this error volumes becomes 2 to the minus 4 at this point. And this is minus y. So we assume this is larger, so plus. And this is smaller, so minus. So this means that this is smaller errors, and this is larger errors. And interestingly, for example, this is larger here. So this is larger of this coefficient. And this is smaller of this coefficient. And because the error amount is same, larger and smaller, but the amount is same, which means that these are cancelled here. So we have these values. So we add this, and then becomes half. So by calculating this, so we can calculate the impact of this error at here. So for each mixing operations, we assume errors and calculate these values. And we sum up the values at the final destinations. So we sum up for this red case and also blue case, but note that these errors are different scenarios, so we don't sum together, but we differently add these cases. So for example, in this case, we consider this and this separately, and we consider the total value of this. And these values works very well. That is, so we can calculate these values for each graphs. And so this is the experimental results. Maybe I skip. Okay, so we assume the error happens with these probabilities of these splitting errors, and we simulate the given graphs and calculate the expected error values for each graphs. And here, what does this mean? That so for these target considerations, we use the graph generated by Lemire, and this means that so for there are so many candidate graphs. So we check all the graphs and calculate the error values for all the graphs. And this is the best error values. And this is the worst error values. And this is the average. And here, actually, we just select one which is with the best RRE values. So this means that we can find the best ones. So, okay, so I think this is the last of my talk. So I'm sure if you have any questions. Okay.
So this method requires knowing which split is bigger, right?
Yes, so we need a camera, but we don't need redo operations. So I think maybe we cannot do any more good way for fault random way for this kind of biochip design. But there is another kind of biochip called MEDA. So here this device can mix one by one. But for MEDA, we can mix any ratios, 2 by 3 or much more variations. So for that kind of MEDA, maybe we can extend this work. So I'm considering that. Please.
So can the capacity for the mixing be increased instead of one drop? Can they add 2 drops, or is that not possible?
Oh, sorry, I can't.
So when you mix drops, right, you take it as 1 drop and 1 drop for one chip. But can that be increased to multiple drops for mixing?
So for this device, we cannot do that. But there is another type of device which is called MEDA. Then they can move any volume, not any, but many types of volumes. So 1 by 2 can be mixed or something. So maybe that's interesting to consider that device. So, not sure. Any other questions or comments? Or any question for Japan or I don't know.
You mentioned in the first slide that the applications of this include DNA sequencing. So can you elaborate on that?
Operate on that? What do you mean? DNA sequencing?
How can it be done?
Oh, I'm not sure, but there is a protocol for DNA sequencing graph. So, yeah, some paper says we can do that on this device. So sorry, I don't know the detail.
Please, sir, have a seat.
Thank you, Professor Yamashita, for that insightful and thought-provoking presentation. We are privileged to have had the opportunity to learn from your expertise.
We now invite Dr. Ankur Gupta to deliver the vote of thanks.
Good afternoon, everyone. It is my privilege to deliver the vote of thanks at the conclusion of this enlightening session. On behalf of NSUT, I extend my heartfelt gratitude to our esteemed guest speaker, Professor Shigeru Yamashita, for sharing his profound knowledge and insights. Professor Yamashita, your groundbreaking research and innovative strategies have not only deepened our understanding of this critical field, but have also inspired us to think beyond conventional approaches. We are truly honored to have had the opportunity to learn from your expertise. I would also like to take this opportunity to thank our HVC, Professor Anand Srivastav, for his visionary leadership and continuous encouragement that enables us to host such impactful events. I would like to express my sincere appreciation to all the faculty members, staff, and students who joined us today and contributed to the success of this event. Your enthusiasm and participation make gatherings like these truly meaningful. Finally, a big thank you to the organizing team, my scholars, my research mates, for their tireless efforts in ensuring the seamless execution of today's session. Once again, thank you everyone for being us today. Wishing you all continued success in your endeavors. Thank you.
Thank you, Dr. Ankur Gupta, for your kind words and the thoughtful vote of thanks.
As a gesture for our deep appreciation for his invaluable contribution, Dr. Ankur Gupta will now present a book to Professor Shigeru Yamashita.
We would like to express our heartfelt gratitude to Professor Yamashita once again for delivering such an insightful and enriching session.
This brings us to the conclusion of today's session. We sincerely thank you all for your participation and engagement. We hope you found the session both enlightening and inspiring. Have a wonderful day ahead.
Thank you.